Okay, welcome to lesson 30. We're going to talk about the robustness of T procedures. So basically we're going to talk about how well do the T procedures do when we don't meet, especially size requirements. So looking here, the idea of robust or robustness, we want to know, are the results of our test still valid if we don't meet all of those conditions? So we had those three conditions that we needed to meet for all three different T procedures we just did. If we don't meet them, what happens? And they definitely aren't going to perform as well when the size requirement's not met and you have strong skewness in the data. So we're just going to look at different scenarios here. It is important the data are from a random sample so that they represent the population we're making a statement about. In general, we like our sample sizes to be, bigger if we can, but if you have some skewness, you're going to want samples definitely bigger than 15. If your samples are smaller than 15, they need to appear roughly normal. So if you have a sample size of 15 or smaller, you should probably throw it into a histogram, make sure that it looks roughly normal. Otherwise, this may not be the best procedure to use. We do have other procedures that could be used. So in general, if your sample sizes are from 15 to 29, as long as the sample doesn't have huge outliers or really strong skewness, this should probably be fine. However, if it is really skewed, maybe having a sample of 15 to 29, that's not going to be big enough. And then if you have a sample of 30 or greater, it's not going to matter too much what our data look like. It's going to be a big enough sample that we can still count on things like the central limit theorem kicking and being usable. So here, this is like one sample T procedures in practice. So I have a normal population. So when I go ahead and I take a sample of 14, it's not a huge sample size. It's fairly small, but it's fairly symmetric. I know that it looks a little bumpy here, but it's largely the size of the bins there. So when you go ahead, you run your tests, your sampling distribution is going to be nicely shaped, and your type 1 error is going to be right at whatever you set your significance level to be. That's going to be good. We never want it really going notably higher. If your type 1 error rate is higher than what you're setting it at, this is a problem. So small sample sizes are okay if you know that the population's normal. But here's a one sample T procedure where our population is not normal. It's very skewed. It's not only that, it's skewed right, because our tail is on the right. So when you take a random sample, hey, it's a skewed right random sample as well. It is not approximately normal, and 14 is pretty small. So this is not going to be okay. When you look at our null distribution here, it's not nice, like as bell-shaped and symmetric as it should be. It is a little bit skewed, which ends up resulting in increasing our type 1 error. We do not like that. We don't like our type 1 error being anything different than what we set it to be. It is very, very difficult. Like here, instead of being 0.05, this test is rejecting 7.8% of the time, which is too often. Two sample T procedures. So now you have, in two sample, remember you have two independent populations here. You need to look at the histogram for both of your samples. So sample 1 has its own histogram, sample 2 has its own histogram. And here we're starting off with population 1, population 2. They're both normally distributed, which even though we took really small samples, so we take a sample of 5 from each, it's okay. It's okay because we know that the populations are roughly normal, so we can count on this sampling distribution, or this null distribution, to be okay. So when you run this, your type 1 error rate ends up being alpha, which is what you set it to be, so it's okay. So small sample sizes like 5 are okay if you happen to know that the populations are normally distributed. A lot of times we aren't quite that lucky. 5 is a really small sample size, it would be really hard to tell from these samples alone that, yeah, this is roughly normal. 5 is really hard. So once again, to sample T procedures in practice, we have population 1 and population 2. But this time, they're both really, really skewed. They're both right skewed. So when you take samples of like 30, so note 30 are usually like our cutoff for, oh yeah, it's going to be big enough. Even though these sampled distributions are pretty skewed, the null distribution is going to look okay. It's going to look like that nice bell shape because 30 is big enough for this to kick in. Our type 1 error rate will be approximately where it should be. But now we might want to investigate when it's skewed like this, but we aren't taking big enough samples. So here's another 2 sample T procedure. So I have a a population that is very not normal. It's very right skewed. And then I have a second population that's nice and normal. So quite honestly, sample 2 is fine. A sample of 10 from population 2 is okay. But you might see a sample of 10 from population 1 is not okay. It's not going to work out. So you need both of these samples to be okay. And so even small to moderate sample sizes, you're going to need to have at least 30 from population 1 if you know population 1 is so skewed. And once again, consequences end up being that your type 1 error rate becomes very, very high. Here, it should happen about 5% of the time, but now so you might notice we intentionally grabbed populations where the means are equal. So when you're rejecting here, you're concluding that they don't have the same means, but they do. So type 1 error should be 5% of the time, but it's 14.2. It's almost tripled. It's much, much higher. So keep in mind, larger sample sizes make it a lot easier. You know that you're meeting the size conditions. It's going to be a lot better. In general, if you know you have at least 30 in each sample, it's kind of like sigh of relief. You don't have to necessarily jump through all these hoops to try and figure out, hey, how is the population probably distributed, whatnot. Because looking at this, I'd say, oh, well, that population isn't normal. I don't know what it is, but it's not normal. Looking at this, I would probably say, hey, the population probably is roughly normal. So absolutely becomes way more complicated when you have very small sample sizes. So here are the your turn and R code examples. Give those a go. Let me know as you have questions.